Okay, so there was a very interesting question in Zulip by Sotiris, who is not here, about what's going on with this successor and if we have the right to claim that it is a successor and stuff like that. And I told him that I'll start this lecture answering his question, but this will not happen. I want to do a little bit of other things first, and then we go right back at it. And I want to go way back, like in the second lecture or third, I don't remember, where I claimed that we know this since high school. This is the carrying of functions, and there is something that we have not discussed, which is what this symbol means. I mean, we briefly said an idea about it, but let's establish this now. The idea is that I want to say that two types, let's say types. Two types will be isomorphic, and this will mean that I have a way to translate back and forth. So I have a translation that goes this way, and a translation that goes this way. And I will call this, now which is which? No, this is carry, and this is uncarry. And the exercise here was to check whether we know this since high school, apparently. And I mean, the argument usually you see here is about cardinalities. So it's like if these were sets, and if I ask what's the cardinality of this set and what's the cardinality of this set, we will establish pretty much that the cardinality of A cross B is the cardinality of A times the cardinality of B. Sorry for writing like that. And similarly, we be careful here because the cardinality of A to B ends up being the cardinality of B to the cardinality of A. And when you see this, at least in like high school, you only talk about finite sets, so there's no question about infinite cardinals and stuff like that. Maybe a better notation would be like to denote sets like that and read this B from A, or maybe like that, I don't know, to help you as a mnemonic. Like the arguments are falling down, the inputs to the outputs, but these are like valid arguments to justify notation and observe that, okay, this ends up being a property that we know since forever about multiplication and exponentiation. So this is not what I want to do now. So what I want to do now is define these two, because we met the lambda notation, and for a lot of you this was like a new thing, and some of you maybe I will bore you to death, I hope not. But let's try to define these functions. I will do one to emphasize certain points. I don't know if you can see it well here, but like this color is weaker than this color. The idea is that I can remove them. They are like implicitly they are there, all these parentheses. I will put them back there to discuss their importance, like a psychological importance maybe. So let's define, I will not do both for you, okay, I will do one. Let's define carry. And let's see what is the process of defining a function that is very similar to the way we will be proving theorems. So how do I define functions? Okay, if there's a function from A to B, usually I say something like, okay, f of x is equal that thing, and the idea is that x is something of type A, and the idea is that here I have access to x, I can use it as many times as I like, and the idea is that if I plug something of type A here, the whole thing will become something of type B. Okay, I hope this is very standard and nothing fancy or new. So let's try to do that. Now, I hope you're not getting confused by the fact that I have something like that. So that the type of carry literally is like here, like carry. It has this huge type. And I realize now that I lied because this parenthesis actually, if I see it like that, okay, I need this parenthesis. The way I wrote it earlier, it was not so necessary, so okay, let's put them back in. So these ones should be there, the big ones, okay. Okay, so let's try to define carry this way. It means that, sorry for that. Okay, so usually I would do something, carry of x is equal to something. And the idea is that x will denote something of the type of the input of carry, which is this whole thing. And now I realize that x is a very bad name, right? Because I'm not used to seeing x as someone who denotes these kind of things. These are functions. So I will say, I will give it a more proper, let's say, indicative name. Are we okay with this? Right? Okay. So the carry of f, and I know here that f has this type, is equal to something. And I will define it. Okay, I'm defining this thing. And okay, now I have to produce something of this type. And I look, what kind of elements are in this type? They are functions. And this is the point I realize that I have not told you how we create functions, right? Perfect. So let's open a small parenthesis. Because about the arrow type, we have seen how to introduce it. Sorry, we have seen how to eliminate it. Right? Yeah, okay. So what was the, how do we use it? If we have an f from alpha to beta, and if we have an a of type alpha, I can use it, and we discussed the notation, so I will not repeat the whole thing. This is how we use it, with this invisible space here. It's a bit weird because I keep calling it invisible, and I keep highlighting it like that, but don't get in the habit of writing this little symbol there. It's not there. It's invisible. Okay, so this is how we use an implication. So with the terminology I'm establishing with you, this is like the elimination of the arrow, or the how we use it. And I need to say how we introduce it. And this is like probably the first time that we will realize that these judgments that I'm writing here, they have some invisible stuff that it doesn't make sense to keep writing them every time you want to use an inference rule. And you only write them when you need them, and this is the first time I think that I will need it. So let's see. The idea is that I want to be able to create functions in this situation. If I have an x of type alpha, and from this I can produce some b of type beta, then I can, let's say, turn this x into an argument, parameterize it in a way, and out of nowhere, without actually further things like about x, I can create a function which we know how we denote it. We've seen it in the previous lecture, and I will write like that. And the type of this thing is from alpha to beta. First observation, because before I ask for questions, consider that here in this b expression, there may be occurrences, x may occur here. Sometimes, but unfortunately not always, we are not very consistent with this in the notation. We emphasize this by writing like something like b of x. Okay, but okay, so this is the idea. If I have in my context a variable x of type A, alpha, and with this I can guarantee I can produce a b, then I can say in effect I have a function. Which function? The one that takes something of type alpha and gives me back b, and the idea is that we know which function it is. Like we substitute all the occurrences with the input. It does this. I felt like I didn't have the right to create a function without mentioning this. So, any questions about this? Okay, so it makes some sense. Okay, so now that I have remembered or realized how I produce elements of this type, which is an arrow because of this thing and not because of that thing, okay, I will start saying, okay, it's a function, so I know how to construct it. It's a lambda. Okay, so I will write down lambda. Lambda of some argument. What is the type of this function I'm creating? Someone help me? the type of the argument of lambda. I need someone to say it, not point at it. The type is alpha. Yeah, okay, I said the name, right? Okay, so the type will be alpha, so I will use a name to remind me that it's something of type alpha, and obviously this name is A, okay? And I will add this dot there, and now here, since I'm constructing a function that goes from alpha to this type, this thing here should have this type, the output type of the function that I'm creating, this thing. Okay? Questions? No? Good. Okay. So notice something. The moment I have crossed this line here, I have gained access. So from this point on, then where should I have access to something new, which is an f of type, what is the type of f? Okay, all this thing. I don't know why this became visible again. I thought it's like that. Okay. So inside, I don't know, maybe I should write above here, but from this point, I have access to this f, which has this type. And something interesting happened with this lambda, because now inside this part, I also gain access to something I didn't have out of it, which is an A of type alpha. And my goal here, and I'm using this word on purpose, was to produce something of this type. And I'm starting well here. Now, to finish this off here, my goal has changed. I need to produce something of this type. And since this is a function type as well, I know how to create functions. It's going to be another lambda. Okay, and what happens here? From this point on, I gain access to something that I didn't have out of side of it. I gain access to a B, which is of type vita. And my goal here is to produce something of type gamma. And I guarantee you, if you have taught this thing, and if you don't do all this thing, well, maybe if you do all this thing that I'm doing here, and you ask, what should I put here? What's the most popular answer? Yes? Oh, no, this is the correct answer. This is not the most popular answer. What is the most popular answer? It is a type gamma. Wait, okay. So the type is gamma, but I'm asking what I will write here, right? So I know the type should be gamma. I have lambda A dot lambda B. A is something of type alpha. B is something of type vita. And here I need to produce something of type gamma. The most popular answer is C, right? Okay. And when you complain about that, some people say, oh, come on, why not? But what is the problem here if I write C? You see, yeah? Yeah, who is C? What is C? C came out of nowhere. There is no C in my scope, right? I'm defining a function that, given some argument, which I will call A, returns the function that, given an argument, I will call B, and returns C. This C came out of nowhere, right? Okay, so definitely forget about that, but it's definitely the most common answer here, unfortunately. So now I have to look at my givens and my goal. Let's get into this mindset. I have an F that transforms pairs of alphas and betas into gammas. So I say, probably this will be useful, right? Because I need to produce a gamma. So I can already start approximating the answer. Panos gave it already, which is like f of something. Okay, I don't have something of the type of the input of f. Luckily, I have enough ingredients to compose them, to put them together and create this. So we come finally to the answer that is like AB. And the whole thing type checks, which means all the types are correct, and it means I have satisfied my goal, which was to write something of this type. It doesn't necessarily mean that it's the thing I wanted, but at least it has the correct type. Is everyone okay with this way of defining? Yeah. Δεν υφίσταται το F και ενώ A και ενώ B για το οτιδήποτε. It would be a type error. So, I mean, it exists. So the question is if I could write it, let's say like that, maybe. Okay, so I can write it down, but it's meaningless because I have a type error. Remember that these invisible spaces here associate to the left, which means that this expression is parsed like that, which means that my type error is exactly here, which means that I'm giving to f something of type alpha, but f needs something of type alpha cross beta. So it's a type error to do that. It's not that I don't have access to it yet. It's a type error. So I need to apply f to the correct type of input, and I'm using this constructor of tuples. We have seen this to construct something of type of the correct type. So this is the invisible spaces here, right? The application. I'm applying f to the pair of AB. But you said you had a second question, yeah?
Και μετά τις τελείες υπάρχουν κενά για εφαρμογή
This thing here? This? No. This is not. This is part of the whole thing. The expression I'm using. So this is the function that takes an A and returns this thing. Okay. So I'm not applying the lambda to something. This lambda here is like think of it maybe like for all x something of x. Right? It doesn't make sense to say I'm applying the function for all x to this thing. Αρετή.
Για το γάμμα, ας πούμε, έτσι δεν θα ήταν σαν να βάζαμε οποιοδήποτε γράμμα στο input.
Help me out a bit. What happened? Cloud happened. Okay. Yes. Wait, these types, alpha, beta, gamma, right? They can be any type you like. Natural numbers, persons, functions from groups to whatever. It doesn't matter, any type. So this gamma here refers to this gamma here, right? So I know that my f will produce something of this type. From your look, I think I'm not answering your question. Wait, this thing here has type gamma. Your question is why this thing has type gamma? Do you see it? Maybe no. But look, okay. I think I know what you mean, and I think I will answer it right now. So I have this thing, and your question is why this thing is of valid type. So let's do some type inference. The idea is that I can infer that this. I'm not sure if it's better to do it bottom up or top down. I'll try bottom up. So my goal is to reduce this, to close this thing, to close your doubts, okay? Your doubt is why is this gamma? Okay, so how do I reduce this thing? Okay, this is an application of something. So I have to say how do I create applications, which is the use of arrows, which means I need to have an arrow, and luckily I do, because f has this type. It's an arrow. And I'd better be able to show that its argument has the correct type. So this thing needs to be alpha cross beta. And we are not done yet. Maybe now you can see it, but let's pretend that you can't. Because the thing is not closed yet, right? So this part is already here in my givens, so I have access to it, let's say. But this one, no. So I need to further justify this, construct this. And now I say, okay, this is constructed by this guy. So how do I construct pairs? I look at the introduction of the product here, and I say that I need something of type alpha and something of type B. And luckily, I have these things lying around in my context. They are, because I'm here, right? So I have access to this since I'm inside here. I have access to this since I'm inside here. And I have access to this as well since the point that I crossed this sign, the equation sign. Does that answer your question? Yes? Okay. Okay, so for some reason this I moved it. I should have copied it. So this is f of a b. Further, yes, Maya. Okay, αυτό. This thing. Okay, very nice. Okay, perfect. So, No, not yet. Yeah. So the question is, I will translate and repeat your question, and so that gets recorded as well. So the question is the following: if we define a function like that as well, do we have the right to say that we have established an isomorphism, whatever that means? That was the question? No? Okay. Let me answer this question, okay? I'm pretending a lot, okay? Please don't get mad at me. So the idea is that the answer to this question is no, because these two have to be like faithful translations in the sense that if you go around, it's not like the Google Translate, right? You start from Greek, you translate something to English, you go back to Greek and maybe something different. So this should not happen. So if you carry and then uncarry, you should always come back to the thing you started, and the other way around. If you uncarry and then you carry, you should come back to the thing. So this, if you manage this, you get to say that they are isomorphic. At least for the time being, this will be what I will use. So what is your actual real question?
Όχι, εννοείται, άρα χρησιμοποιούμε το σύμβολο, γιατί άμα κάνουμε την ίδια διαδικασία για την άλλη μεριά, στην πραγματικότητα θα κάνουμε κάτι διαφορετικό, αλλά επειδή εν τέλει πάλι θα πρέπει το αποτέλεσμα ότι θα become something of type gamma, είναι σαν ότι περίπου ταυτίζεται αυτή η διαδικασία μία με την άλλη.
This and this? No, they are not similar, and I mean, you will find out about this when you do this exercise. As I said, I think it's better if I don't do the other side. But if you start writing this, I mean, okay, I will only write the name, like you have the objective here is to define uncarry. You will see that the thing is not exactly similar. It's, okay. Okay.
Απλά, εν τέλει πάλι θα πάρουμε κάτι type gamma.
Okay, so in the end of things, we will end up with something of type gamma, and this depends on where you consider that the end of things is. So this has something to do with the thing I was going to say right now. So maybe this will be, I think it's related to what you're asking, which is the following. Let's say somebody defined carry like that. We are okay with this. We'll have some questions maybe, but this is acceptable. The person who wrote this down definitely liked to see these parentheses, even if they were not required. So the type that this person is visualizing, and now we come to like psychological stuff, which are my favorite stuff, because they matter. So the person who wrote it like that sees the function like this type. And this person wrote down these parentheses, even though they are all these parentheses, even though they are implicit. Maybe didn't write these actually, because, okay. And let's compare this to a different programmer who said, okay, this is very weird. I don't want to write this thing. Come on, give me a break. And whoever has programmed in Haskell or something like that would definitely not definitely, but probably would not do it like that. Say, actually, this is an optional parenthesis. And actually, this is an optional parenthesis as well, right? So if I visualize this like that, the carry function doesn't look like a function from here to there. It looks like a function from here to something from here to something from here to there. And if I visualize it like that, I would say, okay, I will define carry like this. Carry, it's like, now it looks like a ternary function. Carry I need something to denote this type, and this will be obviously f. Now my second carried argument will be something to denote this type, a, and now b, and now I put the stop here, right? And I say that, I have to define this thing, and this thing will be c, and this is a mistake, and this thing will be, and I will do the same thing here, like f of a, b. And if you program one function in Haskell and the other one in Haskell, if I'm not mistaken, it's completely the same thing, because technically Haskell will translate one to the other, which one Haskell prefers. But the psychological thing here is quite different. First of all, you should appreciate that this is much more succinct, like shorter and less digital ink has been spent. But the idea is this is like you visualize carry as a ternary function. It gets a function, an argument, and another argument for this function, and then produces something of type gamma. And you could do something like a middle ground. Maybe you want to put the emphasis here, and in this case, you would say something like carry f of a is equal to, and now you would have say, the function that taking an argument b returns f of a b. Something a bit, I'm getting into details of maybe implementation here, but another difference is that if you write it like that, all your givens, you gain them like simultaneously. The moment you cross this line, suddenly you have all those things. While in this way, there are like three nested scopes, one inside the other. Both things end up defining the same function. This defines it almost directly. The most brutal the most brutal directed way to define carry would be to move this f on the other side and say carry is like a function that taking an f returns the function that taking an a, and you go on like that. Okay, but in this way, actually, you would be visualizing it even without these parentheses, right? Maybe it's kind of extreme, but it's possible. So all these things end up defining the same function. This completely as directly as possible, and this as indirectly as possible. It's way more convenient to do this thing. It's like in a proof, you say, okay, I will prove that this, like an implication or some for alls, give me all those things and I will start proving, instead of saying, give me that, suppose that, give me that. So these things, I'm trying to get you to visualize them kind of similar to the idea of let a of x or suppose this. And there are 1, 2, okay, only 2. If I put like 1, 2, 3, if I'm looking at it like that. Does this make sense? Are we okay with the carry and non-carry? Okay, I haven't finished defending that this is actually an isomorphism, and I will not do it now. But it's a good exercise, and I will assign it as homework. Confirm that this thing ends up where it started, and confirm that this thing ends up where it started, okay? It's a good exercise because you get to see how you apply lambdas to arguments, you do the substitutions, and all those things. Yes?
Ο τύπος του carry είναι το επόμενο, το αλφα βελάκι γάμα.
Wait, are you talking about this or this?
Άμα ο τύπος του carry σχέδιο είναι αυτό που έχουμε γράψει.
Yes, I think so. Yes.
Ωραία. Ο τύπος του carry F είναι η δεξιά παρένθεση. Σωστά.
Carry F, carry F is this, yes. Okay. And carry FA is this, and carry FB is this. Okay. Another question? No, we're fine. Okay. So finally, I think we have some we are starting to see some similarities between the act of defining functions or programming these functions, if you like, and the act of proving things. I have like givens, goal. The whole thing is kind of similar. And eventually we will find out that these things are identical pretty much and not just some metaphor that works well. Okay, so I want to go on now and maybe start talking about the question of Sotiris and go back to induction and recursion. But actually, there is something I want to get away with. I want to be over with. Since the first lecture, I want to look like, because I'm using groups and monoids and stuff like that as examples, algebraic structures. And at some point, I mentioned that probably most definitions you've seen of group technically have a mistake, or they would not compile, as I will say. And I have here like a definition of group, and I would like to try to read it in a very rigid manner, not the whole thing. This is taken from, the first one is from Alufi, it's an excellent algebra book, and the second one also from an excellent algebra book of Herstein. Let's see this one, it's kind of shorter. So it's saying here that a non-empty set, and this gives me an opportunity to rant about the word non-empty, there's too much negativity in this word, like non-empty. Technically, it means that it is not the case that it is empty. And since we're starting to pay attention to those things, if I want to say that it's a set that has elements, I don't want to say it is not the case that it doesn't have elements. It's a double negation. Even if you think it's the same thing, which I hope we appreciate, it doesn't say the same thing. Let's find a different word, and we will call them inhabited. I know it's kind of weird. The first time it's kind of weird, but once you get used to it and you see something like that, okay, you understand what's going on, and you understand that this is probably used as a synonym of inhabited. But let's say stay etymologically valid and call these things inhabited. So it's a different thing. Inhabited means I can produce an element here. Non-empty means that it's impossible that this thing is empty, so that if we derive that it's empty, we can explore the world. It's a very different thing. So I close this little parenthesis again, and let's go back to trying to compile this. Like, let's say these are commands. So I have a set of elements G, and I will say that it's a group if in G there is defined a binary operation. Already the wording is a bit weird here, but this will not be my major complaint here. What do you mean in G? It's an element of G? We understand that no, it's not an element of G. Of course, it's like together with G, there is a binary operation which we call product and we denote by that. And the idea is that the whole thing is a group. And maybe, I don't think this happens in this group, but sometimes you want to emphasize this difference and you elevate, you fancify like your letter G to be kind of calligraphic, and you say, okay, so this is the group, this is the carrier set of the group, as we say, and this is some extra stuff that goes with it. This notation should be familiar to pretty much all of you, I think, yeah. Such that, okay, it's not every time that you have a binary operation you have a group. Such that AB implies that this is that the product is inside of G, and this is like already the first thing that I would argue that it's kind of don't tell this to my friend Mary. This is the first thing that's useless, because if I have some operation here, I need to know its type, and of course I have to give you its type. And of course, its type is what? It's G cross G to G. So this thing is not something I need to check. I already have it by the fact that the type of this thing is this. Okay, so it's the type of this thing. So first I will tell you what are the data of a group, and then we will say what they have to satisfy. So part of the data is that I have this thing. This is not like a law, an axiom that comes afterwards. So like this is the first weird point here. Now, the second one is written as if it's an implication, but for us, it looks better if I say like this. And we will end up writing this only as an equation. Okay? So I will not, it's written in a weird way. It looks like implication while it's not. And I will call them equations, even though technically they are not. They are not technical equations because they have this for all. But if it's just a for all and then equation, we want to write it like that only. And I will abuse like the name maybe, and then we'll just call it an equation because this is how we would write it. I don't like this order. I prefer this. Okay? And so far so good. The first one, I have some I say it's like useless, but it's not wrong. It compiles. The second one, it's written in a weird way. It compiles. The third one does not compile. It compiles. The third one compiles. So what does the third one say? It's an existential. It's not an equation. There is exist an A such that it does some stuff. Such that for all A, something happens. Two equations. Okay, it compiles. I don't like it, but it compiles. Why do I not like it? Because it's not an equation. But, and I don't get to say it's only for all because of this exists here. And this ends up making a huge difference when you study algebra in a more general setting. But okay, technically it compiles. And finally we will come to the fourth part, which does not compile. Can someone tell me why it does not compile? let's read it. For every A, there exists an element, some other name, such that A times this other element is equal to this other element times A, which is also equal to E. What's the problem? I have two hands here, seeing the problem. Maybe three. Arati. Okay, thank you. So this is a question. What do we mean by compiles? Okay, good question. Like when you write a program, the compiler takes this program and like makes it into something that's actually executable, translates your code to something that the machine will understand. And if you have like some weird errors there, syntax errors, or more importantly for us, type errors, the compiler will say, this doesn't compile, you have a type error here, fix it. So I will use this metaphor a lot. Thank you for asking. I thought I had used it already, but this is the first time. It means that technically you have some name error or some type error that it's not that you are stating like something false, like 0 is equal to 5. This compiles, okay? It's meaningful. It's not correct, but it's... So this thing looks like a name, so there's no problem here, because you say for every A, this could be just like a B, okay? Let's consider this like part of the symbol, okay? But the other thing you're saying is like, who the hell is he? And you might say, it got defined in number 3. No, it didn't, because here is an existential, and this E, the scope of this, there exists an E, such that, so here I have access to this E, outside of here I don't. So first of all, like you could say, if you try to write this in a way that compiles, it becomes very ugly, because you would say here, for each A, there exists an A prime, such that there exists some E that is also an identity, and these things happen. I mean, it gets totally messy. And for other reasons that we will come back to this as well, you start appreciating that maybe it was wrong all along to think that group has one protagonist, which is the binary operation, one operation. It has more. You need to shift these guys, actually. I'll do it one by one, to be protagonists in a group, for group theory. The second one will be like this E, or however you want to call it, because now it's part of what the group is. So a group is not just a set, an operation, a binary operation, it's a set, a binary operation, and a denoted guy will say this will be the identity. And you want to do that actually furthermore, even though you might say, why? Because you won't say, actually in the group I have another operation, a unary operation, which is like taking inverses. You may call it like that, or inv, or I don't know how you want to call it. And now you finally have the correct definition of a group, and I will try to defend this word correct, like it's not Thanos likes it, so it's correct. It's a good definition, I think, for correctness. But okay, let's see. Now, part of my data is this, all these guys. I know the types of these guys, so this thing is G cross G to G. The type of E is G. Yes. And the type of inv, or -1, how you want to call it, is... Yes, it's from G to G. Okay? So you have a carrier set together with operations, not relations, operations. And now you have the chances of having the right to call this an algebra. If you write it like that, you will not yet have the right to say that. You have one more obligation, that all the laws you will state about it will be equations. No for all exists, not negations, not implications, only equations. This is the definition of what an algebra is for our in our neighborhoods. Let's say that it has nothing to do with the word algebra sometimes used in like representation theory or like that, which is a specific kind of mathematical structure. And now that you have this, like you can ask if a group is an algebra, and in that it turns out to be a properly algebraic structure. It's an equational. I don't know if if I should call it equational, but okay, it has equations, operations and equations. And where are these equations? Like they are kind of hidden here. There are a lot. Because if you think there are only 3, you are mistaken because these are conjunctions. So I need to write these equations. A, it's a left inverse, so it satisfies this. It's a right inverse, so it satisfies this. And how should I write the other one? Inv A with A, this is E, and A inv A is also E. So how many equations are here? Like 1, 2, 3, 4 equations. And associativity, another one, so it's 5. Okay, so I have like 1, 2, 3, 4 pieces of data and 5 laws. And as a teaser, to make you see something like interesting, the way we will do it in type theory, even those things will become part of the structure. So for the time being, I can ask a group, what's the product of this element and that element? And the group will provide me for an answer. I can ask the group, who is the identity here? It's that guy. I can ask the group, who is the inverse of this guy? It's that guy. And we'll see that I will be able to also ask the group, what is your proof of your associativity? Oh, it's here. So I have, together with here, a proof of the associativity of the binary operation, a proof of the fact that E is indeed an identity for this operation, and here, a proof that, in fact, the function inv returns the inverse of its input. Okay, so there will be like, okay, so and more, 2 more because we saw that there are 5 equations here, right? Okay, so this will happen like in not in the next lecture, like in like 2 or 3 weeks. It should be a bit strange, but it's very convenient. If you have programmed in something like with maybe object-oriented programming, you might appreciate some kind of syntax. So we have the operation, the group carries its operation with it. And the group carries also the associativity of itself with it. And the identity law with it and the inverse law with it. Okay? So, and for a certain group, I may have different proofs for these things, if that makes sense. So, let's take a break. Okay, so I have managed to irritate you enough to keep arguing about this. So, okay, I will have to say a few more things. My idea was that we will see this thing a bit later on when we will start to implement groups. Like, so there are some questions that you asked during the break. Why include all those 3? Okay, why not stop here? Or maybe stop here, okay, and whether it matters. So the thing I want to say now is that whoever you deem to be the real protagonists of groups determines the other important things, algebraic things, which is namely homomorphisms and sub-things. Like in groups, the sub-things are subgroups, okay? And it will be maybe a harder thing for me to convince you about this, because when you see like the definition of a homomorphism in groups, okay, can somebody tell me what a homomorphism is? Like, okay, you start definition, you want to define, you say something like let's say G and H be groups. And then I want to define, and also I have something that helps me go from G to H. I write like that. And now I'm already kind of not being very careful here, because technically this is, I don't have the right to write this as well, because it doesn't get me from the group G to the group H. Technically it gets me from the carrier of G to the carrier of H, so it's just a function. Or if you like my convention of making less fancy symbols, it gives me from normal G to plane H, such that, and then it has to do something. What does it have to do? Somebody help me? Yes? No. Homomorphism. Homomorphismo. It's a homomorphism. Okay. we say that it respects the operation. It respects like the heart of the group, okay? So this means, if I translate it, that phi of AB is equal to phi of A times phi of B. And that's it. And that's it. And if your definition of group is like Herstein's, this should be the correct definition. If your definition is the one I'm proposing here, I'm defending here, you say, wait a minute, it's not just an operation, there's not only one protagonist here. You have a bunch of operations, and to have the right to call it an homomorphism, you have to respect all the operations. So already seems that if I define it like that, let's say my friend Mary Hluberaki is defining like that, what an homomorphism means, and the way I have defined groups, I have my phi has to satisfy more things. Definitely it has to satisfy this thing. It has to respect this, but also it has to respect the identity, which means that the identity of these guys, it's not the same A. I mean, you're used to this thing. I don't need to, like, this is the G and this is the H, okay? And this is like the inverse thing. Okay. So my phi has to satisfy three things, while the phi of Mary has to satisfy one thing. And probably at the moment you see that this definition in a group theory text, you see our theorem. So here Mary would say the theorem, phi happens to also respect any homomorphism, from G to H, respects the identity, and another theorem respects the inverse. So it looks like the two things are equivalent, and here comes, it's a good example to ask ourselves if equivalent definitions make sense to lose some sleep over which we will take as the definition. And I'm defending that's very important, and there's a correct definition and a wrong definition, even though they just happen by chance to be equivalent in groups. Okay. So what I would do here, after defining this, I don't want, studying group theory, every time I want to prove that something is a homomorphism, I will have to do three things, while my friend will have to do one thing, right? So I will prove it, my theorem will be what we call criterion. And I say, look, if you have a function that respects the operation in a group, then it respects the identity. And another criterion that if it also respects the inverses. So my definition will have three things, but I've proved theorems that help me gain this thing, the right to call something a homomorphism, just by proving one thing. This is the whole concept of criterions, okay, criteria, whatever. So it's not like every time I want to prove that something is a homomorphism, I will have to do three things and my friend has to do one. I will also invoke my criterion that says if you guarantee that it respects the operation, then it has to respect the rest of the thing. But the correct definition of what a homomorphism is it respects the structure. And this makes sense in any algebraic structure. It makes sense to say to have a notion of things that respect the structure, and they are called homomorphisms. And it is not always that you can get away with this thing. It's like, as if like by some chance, in groups, it's enough, even if you say it like that, if you respect this, you are the rest of the axioms that you have and the equations that you have guarantee that you will respect this as well. But if you go to some other algebraic structure, this will not be the case. And I will just give the names of this because they are not as famous as groups in the mathematics department. But like if you stop here, you have what is called a monoid, and if you stop here, you have what is called a semigroup. This also indicates how much more famous groups are. So this means that I know what a monoid homomorphism means. It means it's between monoids. It means it respects everything that it has to respect. I will not keep changing my definition when I enter a setting where this criteria will not work anymore. And I will leave it as an exercise, and please solve it and discuss this. It's not difficult. For monoids, for example, you don't have this property. So if my friend Mary was teaching monoid theory, we would end up discussing things and getting in fights. So as a hint, I will give the criterion here, which is that if phi respects the operation of the monoid, and phi is surjective, by the way, we call this surjective homomorphism. This is the correct name for that. So if it does that, it's forced to respect the identity as well. And you may, first of all, prove this, okay, as an exercise. And this is also a very good hint as to where to look for counterexamples in monoids where this thing will not happen. Obviously, the homomorphism should not be surjective. So the objective here would be to find like two monoids and an homomorphism that respects the operation but does not respect the identity. So now it becomes even more essential to use the correct definition and see how it manifests in each algebraic structure. I don't want every time that I study new algebraic structure redefine what homomorphism means. Okay, so this is why it's important to realize which are, I don't know if I'm starting to convince Manolis a bit, which deserve the name, these are the protagonists here. If you are using only the operation and the identity, and you don't really care about inverses, you are studying monoids, and homomorphism there means you respect these things. And like subgroup means these two things are closed. It's closed under those two things. The moment you say, I care about inverse as well, it means, first of all, add the inverse there so that we can see it. And all these things that you were saying, homomorphism and sub thing, now means something different, have extra burden. You get away with it in groups by chance. You get away with it in rings, maybe by chance, and so on and so forth. We'll probably discuss this a bit more when we implement this in, play with this in Lean to see how we do group theory in Lean and monoid theory and stuff like that. And you start, since I mentioned I started from group and I start chopping things off. From semi-group, if you chop the only thing you have, which is associativity, you are just left with a set and a binary operation with no laws, and this is called the magma, and you cannot prove many things, obviously, because you have nothing. On the other hand, you have many more models, there are a lot of magmas around. But don't think this is like one way around. Another nice exercise is to see what goes if you try to add inverses without having identities. And this might seem nonsensical because even to state the word inverse, I need access to an identity, but I don't. And so this is another homework to think. Try to figure out what an algebraic structure would be that has a binary operation, associative, why not, and has inverses, but it doesn't guarantee an identity element. But I have dwelled in this what was to be a tiny parenthesis for too long. So let's. Is it okay? We have closed this parenthesis a lot and go back to answering the question of Sotiris and talk a bit about induction recursion. Manolis, what's your? I might redirect you to Zulip, and you will ignore me. But okay, go on.
So I feel like the need to be as general as we're trying to be and say that okay, to be a homomorphism and has to respect the structure basically would be more reasonable if we were generally trying to define what an algebraic structure is. It's a set with some operations and some
equations.
Special elements.
Equations. Some operation equations.
Operations and some elements. Special elements. Such that certain things hold, certain equations maybe.
Okay.
So in that case, then yeah, sure, to be an algebraic structure, to be a homomorphism between a certain kind of algebraic structures, we would need everything to be satisfied properly. But since in this case it happens to
in groups
to be something, we want our definitions to be as simple as possible. And
this is the philosophical thing where I say this is like you should not. Maybe you disagree there. It's not really. This thing I'm saying is not a theorem. Okay, you should not try to get the shortest definition possible. You want a definition that captures better the idea you're trying to describe. This was like my quarrel the first time I saw Zermelo's actions. I was taking a set theory course with Moskovakis here. And the first axiom was like there exists a set without elements. It's like the existence of the empty set. And I remember I asked him about that, like, why not say there exists a set? Because with the rest of the axioms, like you have the separation axiom, and you can say like, give me this set. I don't know so far that it's empty, and give me all the elements that are not equal to themselves of the set. And you have constructed the empty. And someone say, okay, so you are asking your definition for something that is way stronger than what you need. Take the most economical thing. We are not the idea. We want to capture the idea in the best way possible, and we gain like benefits from both sides doing that. Because as I said like 5 minutes ago, I will prove criteria. This is the whole concept of if we went your way, right, we will never use criteria because we would already have the most economical definition. Technically, like the way I see criteria is like things that help me prove a definition in a much shorter way. So they guarantee the thing they need to guarantee in a shorter way. I will use these theorems, but they are not definitions. Like, because I need to communicate, and the moment I will start talking with a monoid theorist, we will say, what do you mean by homomorphism? It's a different thing here. Here I have to say that it respects the identity while you get away with it by chance. Let's agree that we have to be careful about which the protagonists are, and that homomorphism has to respect everything. And once you go inside and start studying group theory, try to find whether you have criteria to satisfy like what a subgroup is. It's the same thing with the subgroup. In the subgroup group theory, you say what? It's a subgroup if it's closed under the binary operation. What about the other things? You get them by chance. Okay? So actually, a subgroup is something that's closed by all three operations that you have in a group. And this definition will not change when you start talking to a ring theorist or to a monoid theorist or to a semi-group theorist or whatever. It's like, in this sense, I'm defending it as the correct definition. Otherwise, you're abusing notation. And it's the same thing since you mentioned monomorphism, and I said we will call this an injective homomorphism. This we will see it like when we do a bit of category theory. It's wrong to think that monomorphism means injective homomorphisms. This is a theorem. So we'll see categories where, okay, I'm irritating Manolis a lot. I like this. And the same thing for epimorphism. So in certain categories... Okay. So whether in a world setting, like a category, or you're doing groups, again, it just happens in groups that injective homomorphisms are monomorphisms. We'll meet the definition of monomorphisms, the correct definition of monomorphisms, and similarly for epimorphism, and we will prove as theorems, look, in groups, an homomorphism is injective if and only if it's a monomorphism. This becomes a theorem. It's not like a short, fancy Greek word to describe this.
Every structure I've seen where we've talked about monomorphisms, for example, it's defined as...
I know, and this is why there's a huge class. The moment you start appreciating the vocabulary of category theory, you feel this kind of anger, like you gave me the wrong definitions, because all this time I was taught to believe that this means that, while actually this is a theorem. It happens to be that in these things that we're studying here. But like, monoid is a good example. For monoids, again, it's not the same thing. We will have this as an exercise. Like, find an injective I don't want to give too much of a hint. Like, either find or both, or at least one of the two you will find. You will try to do it. Something that satisfies injective homomorphism, but does not satisfy monomorphism. Okay? It happens in groups. You can say, I would like to get you all to say that it's wrong to say I don't care about the definition. Like, care about the definition, even if you have the comfort or like blindsidedness maybe that you don't care of things outside your world, and you say, I will call them monomorphism. Because at the moment you step outside, these are not guaranteed anymore. Okay? So I'm closing this parenthesis here. I managed to irritate you. I don't know if this means nobody will come back here, or you will want to reach the point that we'll start understanding the reasoning behind these things as well. One more thing that I want to irritate you on with one more aspect. So I emphasize the operations and equations. Manolis mentioned elements like constants as well, like the identity. We will see them as operations, and I think this will not irritate anyone. It's like an operation that gets no arguments and gives you back the identity. It's like zero-ary operations. Especially in programming, you are very used to see something like you call an f with nothing, and so this will just be an element of B, and you say, okay, let's identify this. Okay, so the constants, I consider them like a special kind of operations, zero-ary operations. Okay, so operations and equations. Okay, so the idea is that if you describe the laws of group theory without, not in this form, operations, equations, but in your laws you have like for all exists implies there is no such thing, blah blah. You lose the right to say that this is an algebra, and you can regain it if you manage to rewrite it in the form with equations. So I cannot say that what Herstein or Mary does there is not algebra in groups, because they can say, okay, but you can you reformulate it in a way, and you will have equivalent structures there, equivalent theories. So group theory is indeed an algebraic equational theory, even though presented the way it's presented most of the times, it's not obvious, it's not immediate. You have to say, you start looking, can I find this, and can I write this as an equation? Like, the conjunction is very simple, like, because if you have as a law AE equals A, something like that, AE equals A, and like EA is equal to A, and if you only want equations, okay, how do you do it? Yes?
Substitution.
No, wait, substitution what? With what?
Αντικατάσταση.
Yeah, I got what you mean, but wait, like you see this as a law, and your weird professor's problem, teacher's problem, which it's me here, he only likes equations. So this is not an equation, it's a conjunction. Okay, but it's very easy to solve this problem. How do you do that?
You get two equations.
Yeah, now you have equations, right? And the same with the inverse, right? But if you didn't have the inverse here, you would have a problem. If you didn't have the inverse inside here, as a named thing inside your group, you would not be able to do it. But you say, okay, I'll put it there and I'll get an equivalent thing, okay? For rings, unless you are some weird person that wants this in a ring to be valid, you get away with it. You don't get away with it, but you can reformulate it in only equational things. So ring is an algebraic structure, and ring theory is an algebraic theory. Just to irritate you and stop with irritating you for today, with fields you cannot. So tell your field theorist friends that they are not doing algebra in this sense. It's not an algebraic equational theory. It's it's a nice challenge. Like, how do you prove that? Because groups initially seemed that they also are not equational, but thinking a bit, we managed to define it in a way that only uses operations and equations, which apparently is the new definition of algebra. Okay, let's call it just to not fight with the names. Let's say, okay, they're doing algebra, but it's not equational algebra. Okay, so why the fields are? This should be a theorem, and it's a good challenge to try to think, how would I prove it? You need to prove that there is no way to formulate field theory using only equations. And usually when you have to do things like that, you prove that when you stay within these ideas of algebra, certain things hold, and it's sufficient to find one of those things for fields that is not valid and say, oh, therefore, I will not lose my time trying to put this into this weird format that this weird guy wants. Okay. So quickly, no more questions. You ask whatever you want in Zulip, and we take it there. I need to speak a little bit about recursion and induction, because I think most mathematicians have not seen induction and recursion in this sense, and I have already defined the natural numbers. The very important question by Sotiris was this: do I get to call this a successor? Because so far it seems like it's a function. So the first point I want to make is that I'm calling them constructors for a reason. So this thing, it looks like function application, and indeed for every constructor I get to use it as a function as well, but the two things are not synonym. The big difference is that it doesn't make sense. Okay, if I have a function f like this, it makes sense to ask how much is 3 plus 2, or how much is the factorial of 3. You apply the definition, do the calculations, and you find out that the factorial of 3 is 6. The question makes sense. It doesn't make sense to ask what is the successor of 0. This is already a fully computed thing, a canonical value of the natural numbers. Same thing here. It doesn't make sense to ask what is the successor of 0. You may be tempted to say this is equal to 2, but actually this is what 2 means. I'm defining like this weird symbol to be syntactic sugar for this thing. So if you ask like someone how much is the successor of 1, it's like the same thing as asking them how much is 42. 42 is already a value. There is no further computation. And this is the importance of what, and some other things that we'll meet, of what differentiates a constructor. The constructor, when given proper values, canonical values, it's already a value. There's no further computation to happen. So this is an important difference and why it's not merely functions. And now I want to see what induction does for the natural numbers and forget maybe a poem we learn in high school. I'm sure we learned this in high school, not elementary school. Like 3 little steps for you to prove something by induction. Okay, forget these 3 little steps because they are not 3, they are 2. Okay, let's see why. So how induction works for the natural numbers. First of all, in order to do induction, my proof has to have this form. I'm trying to prove something for all natural numbers. Whatever this phi is, we know that the type of phi is not to prove. Eventually, we'll see that these types are not very descriptive, and we'll have to try to say more within the type. Do I have a mistake? No? No. Okay. So, by applying the rule of induction, I get to reduce this goal to 2 new goals, okay? So the first thing is I need to establish that this round symbol, okay, has this property. And the other thing, I will write like that, like this. For all k, I could use n here, but just for the aid, in this case, I will use k. For all k, again of type nut, if it so happens that phi of k, then phi of successor of k. So in our system that we're, like in our language that we're developing, I'm introducing a new command which is called induction. Just induction full stop. It is only executable, if your goal has this form. For each natural number n, something happens. If this is like that, you get to say induction, and what is the effect? Your givens do not change. You split, you have 2 things to prove. In the first one, with the same givens, this is your goal. In the second one, with the same givens, this is your goal. So we tend to call them base and inductive step. So I will do it like that. Base means this guy. This is the base, and it means I have to prove this, obviously. And the nickname of the other part is the inductive step. Please don't call it inductive case, but okay. There are too many things that eventually you will give up on me, I think. Okay, so like inductive step. And here I have nothing to say, just look what this means and prove it. While here, I already know enough of the form of this goal to know how to attack it, how to start my proof here. What would the first command inside here be? Suggestions? Yes, Maya?
Let k be none.
Okay. And you can choose actually any name you want, right? I use something different. Just, it's not to irritate this time, but just to keep aware of the substitution that I have to do. Not, and what is my goal here after this let? So here my goal was phi. At this point my goal was, I had some data, I don't know, I had some givens here, gamma, and I was trying to prove for all n phi of n. I did induction, so inside here I still have my gamma, the way it is, and now I have to prove phi of 0. And here I still have my gamma, and I have to prove, okay, I need some space here. I have to prove for all k, if phi of k, then phi of successor of k. Okay, so I have all the givens I had, and now I also have t, which is of type nat, and I also have something else. No, not yet. I will gain something else in a minute. So here I have to prove that phi of t implies phi of successor of t. Does that make sense? I did this on purpose. We will not do that, but it's like the first or second time we are seeing this, so I want to get used to the idea of I need to substitute these things to get the correct goal. Okay, so next line. Arati? Yeah, suppose we have already found out that technically suppose is just suppose, right? But okay, let's write it like that. Suppose phi of t, and now like what happens is this guy comes here. Forget this guy, and it's like that, okay? So, a lot of times, what we want to prove has this form. For all something, if this, then that. Let's not write these as separate lines. Let's introduce this syntactic sugar. I should be able to write let t nat such that phi of t. So this is just a shortcut for these two lines. I'm doing like a combo hit, like these two moves, and I'm right here, okay? I hope we appreciate the readability of this thing. Okay, and now my goal is to prove this. So essentially, I will manage to prove this if I close these things, these goals, okay? Now, you can say that this is like some weird axiom that I want as an extra for the natural numbers, and I want to argue against this, and I want to say that actually try to understand what's going on here, and what would be the correct formulation for induction, because maybe you are in a type that has no idea what 0 means and what successor means, and instead of defining induction to be intimately related with these things, you want to liberate the idea of induction, capture the correct meaning of what induction is, so that it applies further on to other types, so you will not have to define what induction means in every type you do. You get it for free. So just a second, I would like to say why, okay, first of all, why are there two things here? And this it's not three, okay, it's two. Why are they two? What else is 2? That if it was 5, this would be 5. Yes? Very, very well. So the constructors of this inductive type, as it's called, are 2. These two, the 0 and the successor. So I want to understand this rule here, not as a special property of the natural numbers, but in a general way that will apply to other things as well. So here, I will say that I want to find good names for these two branches, okay? So the good name for this one, you may have other suggestions, I'm open, is that this constructor preserves or respects phi. It's not an operation, it's a property. And this one will not change at all. I will just copy and paste this and change the name of the constructor. And finally, I can say, okay, maybe I need to say what preserves and respects mean, but finally I can put the idea of induction in the framework, show that all constructors respect your property. If you are in a type that, like the natural numbers that only has two constructors, you need to show that they respect this property. And what is the idea? Let's try to see what this means, right? The respecting something. It will end up meaning this, okay, obviously. But let's see it from the point of view of the successor. You are interested for some reason in this property phi. Let's call things that have the property phi nice things, beautiful things, okay? So, it's not that the successor should only construct beautiful things. This would be unfair to the successor. Because maybe you fed the successor some ugly thing. So the responsibility of the successor is that given beautiful things, I will not be the reason that there will be ugly things produced. So let's read it with this mindset. What happens here? For any natural number, if this natural number has this property, then the successor is required to produce something that has the same property. If you give the successor something that doesn't have this property, we don't care what it does. It can create something beautiful or something ugly. We don't care. It's not its responsibility. It would not be its fault. Okay? Does that make sense? Is it a bit too metaphorical, social? I don't know, but I think it works. So right now, let's define one more type, which will be inductive type. Not so interesting type, actually extremely interesting, but not so interesting in the inductive way. Let's define the booleans. I don't have booleans so far, okay? So let's call them bool. Ideas of how I would define the booleans. Pick any of the three nice ways. We have three nice ways, okay? Either tell me the rules, or the constructors and their types, or the forms that a boolean must have. Like, Arati, which of the three you prefer? This one? Okay, valid. So how would you say it? Okay. I saw you doing that. This is why I will write that. Okay, let's call this, I don't know, like true. We have to pick a name for our booleans, and I will use a double T, because a lot of times I will write like something like that, and I don't want to confuse it with the boolean value that I'm constructing here, and the type of this, which is bool, of course, and I need one more constructor, right? Exactly. Okay, I hope I'm not doing weird stuff. But finally, I'm enriching my types, right? I now have the booleans. And I don't get the right actually to say that I have finished my work with the natural numbers because I haven't told you yet how to use them. Like we've seen how to introduce them. They have two ways to introduce them. It's like this, either by that or by this. No other way to create natural numbers. But how do I use them? This is not something we have not seen. And similar here. Like I'm saying how to introduce them. I have not told you how to use them, the booleans. Can anyone guess what the use of booleans is? One, two, yes.
Σαν την εικόνα που είναι μια συνάρτηση από proposition σε κάτι.
No, you are trying to answer a different question, like how we would maybe implement them, like define them if we had something else. We don't need to do that. We are implementing them right now, okay? So like, these two guys appeared there. Now, how they behave, we need to do some more work for that. But we already have this type. It has two elements. So far, I just have them. They're not so much useful. What was your answer?
Yeah, I think
pretty much something similar.
function that takes.
It's the if then else. This is how you use booleans, okay? Let's see this. I could write it like if then else, all one word, but it's ugly. So like if you have a boolean b, the way to use it is you also have something of some type, I don't know, let's call it gamma maybe, I don't know. I will call it a y of type, let's say alpha, okay. And then n of type alpha. And if you have all those things, you get to form this branching thing that's like if B, then Y, else X, and all this thing. What is the type of this thing? Somebody? Yes? No, it's not bool necessarily. It could be, maybe, but yes? Alpha, right? So this is, because, look, the Y and the X here have the type alpha. And so this whole expression is something that once you evaluate it, it will look on the Boolean. This is how you use a Boolean. You look at it, and you get the information if it's this guy or that guy, and correspondingly you get the right to become this or that. So this is the use of Booleans. If the Booleans were only one guy, you would not get to do that, because there would not be information carried together with it to decide anything. Imagine a Boolean with only one thing there. It's not useless. It's like the next type we will define. It's extremely useful, and I promise you that when I ask you if you have used this or seen this, you will say no, but you will be lying without knowing it. It's okay, so technically it's not a lie. But I think, so anyway. So, we would like eventually something similar for the natural numbers. How do we use them? And the idea is pretty much this. This is how you use the natural numbers. But we'll have to defend this, and I will not do this in the next 5 minutes. So, I'm introducing the Booleans. We saw how to use them and how to introduce them. What's missing? And this is kind of simple for the Booleans, so let's do it. I have given you what things there are, how to create, blah, blah. I haven't told you how these things compute. Equations, vita and eta. So I won't, as I told you, we'll not spend a lot of time trying to define what vita and eta means, but we'll see it so many times that it will get in our blood somehow by osmosis. So any guesses for what the vita should be here? I want something that reduces thing and goes on with the computation, and it involves Booleans, obviously. You have a suggestion? You have no, wait. So another thing that is okay. Panos is going in a different direction, saying about not and maybe the Boolean and the Boolean ors. These also give Booleans their like it's the soul, like the operations of the Booleans, but they are not primitive things. I will define the Booleans.
Κάτι άλλο θα μπορούσαμε να χωρίσει ταυτά και not ταυτά, έτσι εδώ πέρα. Δηλαδή, γιατί προτιμάμε να το κάνουμε διακριτά.
Good question. So, for this moment, the idea is something I haven't mentioned. Maybe I should have mentioned it. I consider that constructors create necessarily distinct things. So. Right now, I know that true and this TT and this FF are different things. If I only had one and I say I'm defining a function of this, I have no way, like this function, let's say your Boolean, let's say I delete this, right? So if you try to define a function, first of all, you have to tell me from where to where it is. And if you say from bool to bool, and you only have this constructor, your not will end up being the identity function. Somehow you want to say that, wait a minute, not is not a function, it's a constructor. So you need to put it in the constructors, and then you realize that it doesn't really have an argument. It's just it just is something. Okay, I'm glad I'm starting to irritating more people. Yeah. Because here I want all these values, I wrote them here, all these values, I want them as like distinct values, and I get that because this is an argument. If I did the same thing on true and I introduced another, let's call it not, right, as a possible constructor from B to B, and now it's a constructor, what I have defined here is like a different version of the natural numbers, because now true is then not true, not true, not, yeah, okay. So it makes sense, I hope. And the other idea was, or was it a similar thing? I'm asking like, what would be the vita things here?
If TT
Perfect.
and Y else X equals Y.
Exactly. So the idea here is I want to say how these things compute. So if you see this thing, y else n. This thing is equal to, say it, sorry? Y, yes. And similarly,
Okay, I think you have a typo.
maybe.
You have an X, you know.
Say it, what the typo?
An X at the bottom of the page. That's why.
Oh, yeah, thank you. Obviously, I'm using y and n here to remind me of yes and no, right? It's not, it has nothing to do with x and y, okay? So, like, if in false, this should be like whatever value you said would be the no value, okay? Okay, and maybe more, I don't want to say interesting, but maybe more difficult, I don't know. What would be the eta rule here? Remember what all the etas we have seen so far were, like for the set was like you have a set and then you consider the set of all those x's such that they belong to that set. You just added wrapping around the machine, like clutter. What was the other eta we saw? The tuple, the product. It's like you have a thing, you extract the left and right, and then you put it back in a thing, and then the idea is you go back to what? These are the uniqueness things. Nobody worked on this yet, and it will be an open homework for some time. Understand why these are called uniqueness. Yes, Lazar, you have an idea?
Yes. If B, then he, else he equals he.
You're approaching it, but we want something better. Okay, wait. Then x else x. Okay, this should definitely hold. But this is what you said, right? Okay, so this is a correct equation, but this is actually an application of, we will be able to prove this, let's say. It's an application of how this thing works. Like you will check B, if you find T, this thing will be replaced by this X because of this Y. So it's like a special case where you have X and X here, you will be able to prove it. So maybe I was like too fast to say yes, because you know now that Lazarus started correctly. Like if B, then we want to capture this idea that you have something, you use it, and then you put it back together, and then you are like exactly where you started, Manolis.
I'm going with the uniqueness aspect more, I guess. So if we have if B then X else Y and X is not the same as Y, then B is true or something like that.
No, you're trying to do some like reasoning again over this. Konstantinos was like was the same similar thing. Say what you're saying. I want an equation. So give me an equation. Okay, I will write the. Okay, I'll try to help you like that. Okay, I want something that I'm given a boolean and I will use it and do something, and in the end I want to end up with the same boolean, right? Okay. So on the right hand side, this should be a B. This is like arguing the way you. So maybe you argue in eliminating multiple choice things, and now maybe it's clearer. What I need to put the. If B, then what do I put here? Yes, Asterios, right? Yes.
Then true, else false.
Exactly. So this is, and I hope this is the third eta thing we're seeing. Bit by bit, we'll start understanding better that these things are eta things, that this are beta things. First of all, this makes sense, right? If B, I know that B is a Boolean, then true, else false. This whole thing is B. And usually a defense, I was saying sometimes like, you would never see that. You would never take a tuple and this thing that Malon's like extract the first part, extract the second part, and then put them back together. So when you write that, it's completely, say, nobody would write. I will never find an expression like that. You would be surprised, unless you have taught programming, how many times you see code like that with not experienced programmers. Writing stuff like if blah blah, then true, else false. Okay, just return this thing. Okay, this is extremely common. So at least we have something that it's not like you are inventing this just to make sense. this thing, actual humans will write it. Not a good programmer would write that. The other thing, humans will not write it, but we will see that it's essential because once you start computing things, you don't have control, you don't know where you will end up. So you will need these rules because at some point these things will show up. No human wrote this thing that Manolis said. But substituting will be generated those things, and we need to simplify them to go on with the computation. And I realize that I'm out of time, so we end here. Like maybe I will give an exercise with the next inductive type, which will be the lists, so that we have something to play with.